Okay, so this week's going to be basically all confidence intervals. So we'll be working through some examples today, kind of trying to give you a really good base understanding. We'll move to Excel later this week, and really we'll be doing this for quite a while. So a couple of things, a couple of resources. Obviously, the lecture slides are kind of up for this week in the lecture slides folder, but in the in-class data folder, we have this CI grade data and the confidence intervals example, right? So we'll be working with both these files this week, primarily using the confidence intervals example. I'll probably show you this file to try to help better your understanding of confidence intervals. Probably, I don't know if we'll get there Wednesday, but for sure on Friday. So kind of have those pulled up and available as well. I'll give you kind of a little bit of a refresher of what we talked about at the end of the day or end of last week on Friday, and then we'll kind of jump into some confidence interval stuff. So what we said we're trying to do with confidence intervals is we don't know where the true population mean is. Right? All we can see is one sample, right? And when we have a sample, we can find a sample mean. So we'll use this sample mean to try to figure out where that population mean is, right? Or to create a range of values that we can say, well, look, the population mean is somewhere within this range. Right? For example, if I see a sample mean income of 55,000, well, the true mean could be 54, and it would be pretty likely for me to see a sample mean of 55,000. Right? That's not that unreasonable. However, it's very unlikely if the true mean was 54,000 that I see a sample mean of 250,000. Right? So I'm going to use that sample mean as kind of a jumping off point. And then I'm going to go a certain amount to the left and the right of it to create a lower and an upper bound to where I can say with 90% confidence, the true mean is somewhere in this range. All right, so maybe, switch the dot cam here. So, maybe I see this sample mean of 55,000. Oh, 55,000. I then say, okay, well, look, with 90% confidence, I could say that the true mean is somewhere within 50 and 60. I don't know what it truly is, but it's, somewhere in this range. Okay? And that's because seeing 55,000, well, that wouldn't make any sense if the true mean was like 150,000, right? So I can kind of create this narrow range of values and say with a certain level of confidence, the true mean is somewhere in this range. So the next couple slides I went through at the end of the last lecture, I'm going to review, but kind of drawing them out myself, and I think hopefully giving you kind of a slightly better idea of what's going on. So let's say I'm thinking about my standard normal distribution. Okay? There is some positive and negative z-score that would give me a certain area in the tail. Okay. Now, I know that if let's say I want a 95% confidence interval, so hopefully I'll connect this in a little bit, but really what we're saying is if I go a certain number of standard deviations above and below that true mean, so whatever this number of standard deviations ends up being, I want it to be such that there's a 95% chance I'm going to see something within this range. Or if there's 0.95 between these two, that means there's 0.05 outside of that range, or 0.025 kind of in each tail here. So I'm working backwards, right? We talked about kind of the inverse transformation and working backwards, but here, all I want to do is take this area that I now know that is what I want in the tail and find the z-score that gives that to me. Now we'll go through this process in a little bit here, but for now, trust me that when we look that up, the z-score that gives me 0.025 in that lower left tail, and then the positive one, there's 0.025 above the positive z-score in that upper right tail, will be 1.96. Right, so negative 1.96 and 1.96 give me 0.025 in both those tails, which means there's 95% chance that I see something within this range, right? Somewhere between those two z-scores. Okay. So really what I'm thinking about, I'm gonna make sure I give myself enough room here. Well, start out here. If I have to redraw it, I can redraw it. So if I think about when I take a sample and I calculate a sample mean, what I know is going to be true about that distribution, as long as I have a sample size over 30, it's going to be normally distributed around whatever that true population mean is. Okay. So if I were to go 1.96 standard deviations, and now I'm dealing with the distribution of my sample mean, so I have to go, the standard deviation of my sample mean, so 1.96 standard deviations above that population mean, and 1.96 standard deviations below it, right? Well, I know that when I turn these into z-scores, right, if I'm 1.96 standard deviations above and below, that'll translate to those z-scores that I wanted of 1.96 and negative 1.96. So the probability that I see from one sample, that's all I can take is one sample, the probability I see a sample mean somewhere in this range is 0.95. And I know that because when I turn those into z-scores, I can find the areas in the tails using the table, and then find the area it's in between as well, or the probability that I'm somewhere in between. Okay. So this is where I'm going to try to put this here. Let's see if we can get this all together. So let's say this is the sample mean that I see, okay? Whatever these numbers end up working out to be. What I'm going to do is build a confidence interval around that sample mean. Now, in practice, I can't see this. I don't know what the true mean is. But I know by the laws of the distribution of our sample means that if I were to build a confidence interval around this sample mean value, so let's say I would go 1.96 standard deviations below that sample mean, 1.96 standard deviations above, well, look, this value is way less than 1.96 standard deviations away from the mean. Right? This value is 1.96 standard deviations away, so this is much closer. So let's say it's like 1 standard deviation away. So if I go 1 standard deviation above, but then negative 1.96 standard deviations below that value, then I'm going to go 1 up, back 1.96. My lower bound is going to be at a point that's past that true mean. So anytime I see a sample mean in this range, when I build a confidence interval around it, well, all these values are less than 1.96 standard deviations away from the true mean. So when I go 1.96 standard deviations below or 1.96 standard deviations above, that's always going to put me kind of past that original population mean. And every sample mean in this range, when I build a confidence interval around it, this confidence interval will always include, right, the value of population mean. So think about it differently. There's a 95% chance that I get a sample mean somewhere in this range, right? Just based off the laws of the distribution of my sample mean. So therefore, when I build confidence intervals for every sample mean in this range, I'm going to be correct in that that range of values includes the true population mean for all these sample means, or 95% of the time. Now, what happens if I saw something, come down here, I'll give myself a little more room. What if I see this as my sample mean, right? Well, that is much further than 1.96 standard deviations away, right? It's actually, let's just say, for example, it's 2.5 standard deviations below. Okay, well now, when I create my upper bound around this sample mean, if it's 2.5 standard deviations below and I only add 1.5 to it, kind of trace up where it's be, it's not quite going to include that true population mean. So for every sample mean out here, I'm more than 1.96 standard deviations away. So when I come back towards that mean, 1.96, I'm not going to quite get to it, right? And so for every sample mean value here, when I build my confidence interval, I'm going to be wrong. Right? That confidence interval won't include my true population mean. But I'll be correct for 95% of them. Now, so like if I could, take go out, I take a sample of 100, calculate a sample mean, build my confidence interval. Go out, take another sample of 100, calculate my sample mean, build another. I do that 1,000 times. 95% of those confidence intervals would include the population mean, and then 5% of them would actually not include it, right? And so that's why after we build these confidence intervals, we're saying, okay, with 95% confidence, the true mean is somewhere in this range of values. Okay? So that's kind of revisiting the discussion that I ended the last kind of class with, or last lecture with. If you want another kind of view of it here, kind of had this one here. We were thinking about we can take any sample mean in this range, and it will include its confidence interval would include the true population mean. Any sample mean value out here wouldn't. Oh, I didn't switch over yet, did I? Getting the slide switched over for class here. Give me 1 second. There we go. So this is the one that we kind of looked at in the last lecture, and that kind of basically what I just drew. Okay. So one thing that we'll start thinking about is this term of alpha. Okay. So I think I have this in the slides backwards from how I like to describe it. But if I have a confidence interval, let's say I want the 95% confidence interval. So that's kind of what I started out with here, 0.95, right? I wanted a confidence interval such that 95% of the time, I'll have a sample mean value where my confidence interval includes the true population mean. So alpha is going to be whatever area is outside my confidence interval. So if I want the 95% confidence interval, there's 5% outside of it, but in decimal form. So for the 95% confidence interval, my alpha, or kind of the total area in my tails here, would have been 0.05, or 5% was outside the interval, and decimal form is 0.05. Same kind of thing. So we come down here. If I had a 90% confidence interval, that means the percent outside the interval is 10%, and decimal form is 0.1. And then I can work backwards as well, right? If I tell you that alpha is 0.01, okay, that means that there's 0.01 total in the tails, which means the area that's not in the tails, or the area in my interval, is 0.99. In percentage form, that's how we say the confidence level, 99%. Okay? It's a little tricky in that, like, if I say, okay, what, 99% confidence level, what is alpha? Well, alpha is not 1%. Alpha is the probability, right? The area in the tail, so 0.01. Okay? So we can work in either direction, but this is what alpha tells us. Alpha essentially tells us what level of confidence we're going to be able to say things at. 90, 95, and 99 are kind of our three conventional benchmark values. Now we can choose whatever alpha we wanted. I could choose alpha to be 0.025. So if alpha is 0.025, what percent confidence level would that be? So that'd be the total area in my tails is 0.025. So the area not in my tails, 97.5% confidence, right? Or 0.975, not in my tails, which means 97.5% confidence. Make sure I have the chat pulled up here. All right, so I want to go through one more concept here. So if we think about different levels of confidence here, well, no, I'll go through this and then we'll come back to that. So the equation that we're going to have for building our confidence interval, I kind of already wrote it out, but this is a more general form. Okay? So we're going to take that sample mean. We're going to go a certain amount above it, right, to get our upper bound. So I added a certain number of standard deviations to get my upper bound. I then subtracted that same number of standard deviations to get my lower bound. So that's kind of like built in, it's like really two formulas here, right? Add this value at the upper bound, subtract this value at the lower bound. Now, for the sake, with the ease of conversation, I think some people in statistics say this isn't technically correct, but it's easy for us to talk about. So what I'm going to call this component here is our margin of error, That's the easiest way to think about it. This is our margin of error. Okay? So, you know, how many standard deviations away do I need to go? Well, here I had it was 1.96, but how did I come up with that? Well, I knew that for the 95% confidence interval, that I wanted 0.95 within the interval and then 0.05 outside of it. The problem is, if I have a lower and upper bound, there's an area to the left and the right of my interval, right? So I kind of can think about this as I have two tails. Alpha is going to be the total area in the tail, so each tail will have alpha over 2. Okay? So I then calculated what alpha over 2 would be. 0.05 divided by 2 is 0.025. Well, here, I know the area in the tail. I know that I'm dealing with a standard normal distribution, or these z-scores. So if I want 0.025 in the tail, what z-score would give that to me? Well, I don't have the z-score yet, so I don't use these row and column headings, right? I actually know the area I want in this tail. So I want 0.025, so I start going through here, 0.005, 0.009. Oh, close. Looks like right here, all right? So 0.025, negative 1.9, scroll up 6, okay? So that z-score of what? Negative 1.96 gives me that area of 0.025 in that lower left tail. So I use the standard normal table to look up what that z-score is. Okay? So, you know, that's how I found that negative 1.96. Now, what did I really do there? Another way I can think about this is, what z-score gave me alpha over 2 in each of those tails, which is what we have here, right? I want to find the z-score that gives me half of alpha in each tail. Now notice, I'll have two z-scores, but that's kind of already built into my formula, right? The positive z-score, right, I add to get my upper bound, and then I use the negative z-score, or I subtract to get my lower bound. Okay? And we'll work through a couple examples here in a second. We're still kind of setting things up. Any questions at this point? Any clarification? Like I said, we'll keep working through these here, but okay. Now, one thing that we'll have to deal with when we eventually get to these problems, excuse me, is we can really write out our confidence interval. Well, I'll use the top part of this. So, oh, the marker's dying on me. Switch colors here. So here was that equation for my confidence interval. But we've talked about, to calculate the standard deviation of my sample means, I have to take the square root of the original variance I sampled from, the original variance of the data I sampled from, divided by the sample size. So we could also write this out, just plug that equation in, and not calculate any kind of intermediate steps. This is kind of similar to some of the examples we did last week, where I said you can do it either way. You can calculate the intermediate value first and then plug it in, or we can just do this all in one big formula. I personally think it's easier to calculate it first. I think it gives us a better idea of what's going on, and hopefully this will come to light as we work through a couple examples today. So here's our confidence interval equations. Let's think about some things that might influence this. Okay? So I believe, let me make sure I didn't forget anything here to remind myself. Yeah, so I have kind of a summary here on these slides, but I want to give you a better understanding of why. So let's kind of start with this guy here. I want to rewrite these just so we can get everything on one line. So I guess I should have just scrapped that paper. So let's say we've got well, remember, this guy here represents standard deviation of our sample means. So I'll try to talk through these intuitively and then show you the mathematical support. So let's say I'm building a 90% confidence interval. Remember, my example was if I saw a sample mean of 55,000, maybe by the time I create my lower and upper bound, it's, 50 to 60,000. So if I can say something with 90% confidence, like let's say I can say with 90% confidence, the true mean is somewhere between 50 and 60,000 based off the sample mean that I found. True population mean is somewhere between 50 and 60,000. Well, if I can say that with 90% confidence, how could I say something with 99%? Well, if I just increase the number of values in that range, like maybe now I say, well, with 99% confidence, I can tell you it's somewhere between 40 and 70,000. Okay, well, I can always just make the interval wider and say things with a higher level of confidence, but that's essentially the intuition behind what we're doing. So if I ever want to say something with a higher level of confidence, that corresponds to what for our alphas? Well, what's the alpha for 90%? 90% confidence interval, alpha would be, so the area outside of the interval is 10%, in decimal form, 0.1 or 0.10. 99% confidence level, my alpha would be 0.01, right? 1% outside the interval in decimal form. So what I would want to do when building this confidence interval is find the z-score that gives me, half of alpha on each side. So for the 90% level, half of alpha over 2 is 0.1 over 2 or 0.05 on each side. So you can kind of think about this area represents alpha, and it's 0.05 on each side. So if I go to a higher confidence level, that means alpha is now going to be 0.01. So instead of 0.05 on each side, I want 0.005. So how can I get a smaller area in the tail? I have to choose larger in absolute value, larger z-scores. So maybe my z-scores I need to get 0.005 in the tails are, somewhere way out here. So if the absolute value, right, my z-scores are getting larger, what's going to happen to my confidence interval? Well, if this gets larger, my margin of error is now a bigger value. So I'm adding and subtracting a bigger value to that mean. I'm going to get a wider interval. So anytime I want a higher level of confidence, that's going to lead to a wider interval. And that was like the intuitive idea, right? I just have a wider range of values. I'm going to be able to say something with a higher level of confidence. Now the next one, first of all, any questions on that before we keep moving here? We good? So the next thing, I'll explain it. It doesn't really matter in the sense that we don't have a lot of control over it, but what if the original variance of the data goes up, right, or is higher? So if the original variance of the data I'm sampling from increases, well, that's going to increase the standard deviation of my sample means, or it's going to increase this margin of error. So I'm adding and subtracting a larger value. It's also going to lead to a wider confidence interval. And that kind of intuitively makes sense as well, because if the original data I'm sampling from has more variation in it, well, it's just going to be harder to pinpoint down that true population mean. And so even if I want to say something at the same level of confidence, when the variance is higher, I'm going to have to include a wider range of values to be able to say, look, I can tell you with 90% confidence it's in this range of values, right? So that one's kind of intuitive, right? If the original data just varies more, we're going to need a wider confidence interval. It's harder to pinpoint down where that population mean is. Now, the one that we do have influence over is our sample size, right? So let's say I take a higher sample size. If I take a greater sample size, what's that going to do to the standard deviation of my sample means? Well, this is where we said, look, the bigger the sample I have, right, the less likely it is I'm going to see these extreme values, right? So, I might see the average income over 10 people is 100,000, but if I take 1 million people, I'm not going to see an average, income of 100,000. So taking higher samples decreases, right, the standard deviation of my sample means, or it decreases this fraction. So if it decreases that fraction, my margin of error is now going to go down. I'm adding and subtracting a smaller value to my sample mean, so my confidence interval is going to be, I guess, more narrow. I feel like narrower is not a word, so we'll throw in more narrow here, okay? So, this one's interesting because we do have a lot of, I shouldn't say we always have influence. We usually can take higher sample sizes, or at least we can attempt to get a larger sample, right? And if we can get a larger sample, well, we can kind of narrow down the range of values where the true mean is going to be, right? Because we can make that confidence interval more narrow. Okay. Any questions on any one of those? Like I said, I have them kind of outlined here in the slide as well, but I wanted to kind of walk through showing you the formula, have kind of the drawing. But all three of those things will change our confidence intervals. Okay? Yeah, okay. So let's go, we got 2 examples that I want to try to get through, and I'll spend a little bit of time on each of them. So the first one is going back to using the birth data. So we know that, let's say, and this is going to be kind of, I think as we work through the next couple classes, this will become apparent that this isn't always going to be the case. But let's say somehow we know the population variance, right? Somehow we know the variance in infant kind of gestation, or the length of a pregnancy, is 9 weeks, right? So we've got a variance of 9. We take a sample of 81 births. We find a sample mean of 38 weeks, right? So what's the 95% confidence interval for where the true population mean lies, right? Well, all we have to do is go off of is our sample. Well, the 95% confidence interval, so our alpha value is going to be what? Right? We want, Yeah, so if we want 95% confidence interval, what we're saying is there's going to be some z-scores such that the probability we're in between that is 0.95, which means that there's alpha total in the tails. So alpha is 0.05, and we have half of alpha in each tail, or like you just said, 0.025. Okay. Now, it's kind of easy. We already looked this one up, right? This was the earlier value. When we go look up 0.025 in that standard normal table, we're always going to find the same value, right? We're always going to find negative 1.96, which would mean that the positive 1.96 would give us the 0.025 in the upper right tail, right? And the way we found that earlier, just as a reminder, we knew that area we wanted in that tail was 0.025. We went to that table. 0.025 is right here. The z-score of negative 1.9, scroll up, 6 would give us that. Okay. So we've got our z-score. Right. Now, if we remember, here's our equation for our confidence interval. Well, it kind of reminds me, oh yeah, I'm just finding the z-score that gives me alpha over 2 in each of my tails. Now, the negative is already kind of built in there, the negative and the positive. So to get my upper bound, I'm going to add this margin of error. To get the lower bound, I'm going to subtract it. So I'm going to go and calculate the intermediate value, which is, okay, well, what's that standard deviation of my sample mean? Well, that's just the square root of the original variance over my sample size. I should say the original variance of the data I sampled from. Just as a reminder, what we had, sample mean was 38, sample size was 81, and I think the original variance was 9. So we get what? 9 over 81 here, which should work out to 1/3. So even though we're going almost 2 standard deviations above and below this mean, the standard deviation is really small. So I'm going to have a pretty narrow confidence interval, and that's because the original variance was pretty low. I took a pretty big sample size, right? So it ends up with a standard deviation on my sample means that's relatively low. At this point, it's just a matter of plugging in our values, right? So our mean was 38. So if I add 1.96 was our z-score. Our standard deviation is 1/3. This will give me my upper bound. And then I use the exact same equation, but I subtract my margin of error. And that would give me my lower bound. Okay? And I'll generally abbreviate them UB and LB, upper bound, lower bound. Okay? Any questions on any part of that process? Okay. So this is the way in which we calculated the intermediate value first. I think this is good because it lets you know right away, I have a pretty small standard deviation. My interval shouldn't be very wide, right? I mean, if my standard deviation is 1/3, even if I go 3 or 4 standard deviations away, it's not going to be very far in absolute terms, right? So if I calculate this and I end up with, you know, my lower and upper bound is going to be, I don't know, 28 and 48, that seems pretty wide, right? Based off of having such a low standard deviation. So it just lets me kind of think about potential kind of values. I don't know. I just think it helps to kind of have a full picture by calculating that intermediate step. But what you could have done, right, is plugged in the equation for what you know will calculate that standard deviation of your sample means. And then from here, you know, to get your upper bound, it would have been 38 plus 1.96 times what? 9/81. And then your lower bound would have been the same thing, but you would have subtracted that margin of error. So you're doing it all at one time here, as opposed to calculating the intermediate value and then plugging it in. But both of these are going to give you the same numbers. Okay? Any questions on that before we keep moving? Okay, so two different ways of doing the same thing. You know, at this point, you know, it's just computation, right? I've got everything plugged in. So go down here, there we go. So we identified everything we needed. We looked up our z-score. We calculated the intermediate step. That's the first way I showed you. You don't necessarily have to do steps 3. You know, you could have jumped right to this equation. But if you find the standard deviation of our sample means, we could have used this form right here. And then it's just a matter of kind of plugging our values in. Okay. Any questions on this before we keep going? Should be all right. So, you know, we could say with 90, no, this is wrong. Alpha was not 0.01, huh? Let me edit this slide real quick. We did the 95% interval, right? So alpha was 0.05. So with 95% confidence, I could say that the true length of a pregnancy is somewhere in this range. I've narrowed it down to almost just a week, right? So it's pretty small interval. So this is really useful, right? If I'm trying to make decisions about kind of, I don't know, you know, when to start thinking about a mother might visit the hospital or something like that, I can narrow that range down pretty good. Okay. Any other questions up to this point? So I'm going to work through one more example here. Let's say, and this might seem kind of trivial. Actually, let me make sure I didn't forget to say something. I don't think I feel like I missed something I wanted to tell you guys. Oh, no, I want to do this on the next one. Okay. So let's say I go over to the rec center. They've got all these weights, and they say they weigh 45 pounds. But, you know, any production process, there's going to be variation in your product. If I'm creating a weight plate, I don't know if this is how it works. If there's someone out there who's an expert, by all means, this is probably sounds dumb. But I think for most people, this would make sense. So they're pouring these plates. Let's just assume they're made purely of metal. You might, you know, have some iron. You might use zinc. You might use, I don't know, probably not magnesium, but some other, you know, kind of raw materials, because some of them weigh more than others. But then you're trying to hit a target weight for your product, but also some of them are cheaper, right? So I have like 3 or 4 different types of metals, kind of all in this, you know, mixture ready to be poured into a mold. So I'm pouring these molds, and some of them end up with a little more iron, some of them end up with a little more zinc, and those have different weights. So there is some variation in how much this product weighs. Right? So I've got somehow have this population variance. I somehow know, like, the machinery, the process they use to create these plates, there's a variance of 25 pounds on it. Right? So I sample 35 of their plates that they made from the rec center, and I find a sample mean of 46.5. So it's a little bit higher than 45, but, you know, with a sample as small as 35, maybe I just ended up getting a couple of those heavier, you know, those weights that were on the heavier or the right side of the distribution, just randomly. And so what's, you know, could I say that with 90, well, hold on. Could I say with a certain level of confidence that the true weight, true mean isn't 45 pounds? Well, let's say we wanted to start building the 90% confidence interval for the population mean. So I already kind of said it, but 90% confidence interval here, because if I want an alpha of 0.1, that means there's 0.1 outside the interval or 0.9 in the interval. But when we talk about confidence levels, right, that's where we usually say it in percentage form. So 0.9 in my interval is the 90% confidence level. Okay? So right away, if I look at these potential answers, I can rule a few of them out right away. So remember, when I build this confidence interval, I'm going to take my sample mean. I'm going to go a certain amount to the left to get my lower bound. I'm going to go that same amount to the right to get my upper bound. So my sample mean should be smack dab in the middle of my confidence interval. If I look at D, 46.5 isn't even in this interval, right? So it doesn't make any sense, right? And if I look at these two, well, one of them, I think it's this one. If I look at 46.5, it's about 2 away from my lower bound, but 3 away from the upper bound. So it's in my interval here, but it's not exactly in the middle, which is where it should be, right? If I'm adding and subtracting the same margin of error to that sample mean, my upper and lower bound should be the same distance from the sample mean, which in this situation, they wouldn't be, right? The upper bound is 3 away from the sample mean. The lower bound is only 2 away. So I can rule B and D out. If I'm throwing darts, I know it's going to be either A or C. Okay? So how could I kind of set this up? Well, what were we told? We got a sample mean of 46.5, sample size of 35 plates that we grabbed. I think just said it, what? Alpha we wanted was 0.1. Okay? And the original variance in the production process was 25. Okay? So, you know, the equation will remind me of this. But the first step is really finding that z-score that gives me alpha over 2 in each tail, right? So what's the z-score that gives me alpha total in these tails, or alpha over 2, right, in each tail? Well, here my alpha is 0.1, so I'm looking for 0.05, okay? So I go to my standard normal table. I know the area I want in this lower left tail, 0.05. Okay. So I'm hunting through these 0.04, 0.05, 0.04. Looks like it's going to be in between these two values, right? I can't find exactly 0.05, but it's somewhere in between these two. So the z-score that would give me 0.05 is somewhere in between negative 1.64 and negative 1.65. So here's why I say we take the larger of those two in absolute value, right? Because negative 1.64 or negative 1.65, negative 1.65 is technically lower because it's less than. So we're taking the higher of absolute value, ignoring the negative sign. So if we're in between 1.64 and 1.65, we're going to use that 1.65 as the z-score, okay? Now, just to kind of mention, let me make sure we have enough time. Yeah, I can mention this. So technically, we can use Excel to get like more precise than 2 decimals. So if I'm in between two like that, I was in between negative 1.64 and negative 1.65, the actual like more precise is negative 1.645. But if I go a little bit further out and take the higher of the two, right, in between negative 1.64 and negative 1.65, I took negative 1.65. I'm going to end up with a slightly smaller area in the tail, which means a smaller alpha and a slightly higher level of confidence. So by taking the higher of the two, I'm kind of erring on the side of caution, right? I'm not only building a confidence interval, I'm saying it's the 90% confidence interval, but technically it's like the 90.001% or something, so a little bit higher. Now at this point, right, we could do the intermediate calculation. So find the standard deviation of our sample means, right? So that was the original variance I sampled from over the sample size. So what, square root of 25 over 35. And I think this is roughly 0.84 if we do that calculation. And now it's just a matter of plugging things in, right? So to get my upper bound, I'll take my sample mean of 46.5. To get my upper bound, I'll add that z-score that I found earlier that gave me alpha over 2 in the tails. And then here, plug in my standard deviation of my sample means. My lower bound is the exact same thing, except I subtract that margin of error or use kind of a negative z-score. Any questions on that before we keep moving? So the other procedure I could have used is instead of calculating that intermediate value for the standard, I almost did it, standard deviation of my sample means, I could have just plugged the equation in for that. And now I've got, my upper bound is 46.5 plus 1.96 times what? The square root of 25 over 35. And then my lower bound would be the same thing, but I would subtract a margin of error. Okay. These will get me the exact same thing. I just kind of broke it down into 2 steps there. Okay. And I said 1.96 here. That's wrong. That was the old example, right? This should be 1.65. Okay. All right. Any questions on that? Yeah, this should have been 1.65. I apologize. I was thinking about the old example. Okay. So I want to go here. I'll show you what the values are, and then we want to add one more thing to the discussion. So, we identified everything we needed. We looked at the z-score. We could calculate the intermediate, do the intermediate step, calculating that standard deviation of our sample means, and then it was just a matter of plugging everything in, right? So once we did that, once we do the computation, we get 45.11 and 47.89. So 45.11 and 47.89, right? So what that's telling us is, right, at the 90% confidence level, right, our alpha was 0.1. So at the 90% confidence interval, right, we built this around our sample mean of 46.5. With 90% confidence, the true population mean is somewhere between these values, right? Somewhere in here. I don't know where it's at. It could be here, it could be over here. The problem is these weight plates were supposed to weigh how much? Right? The company is claiming that they weigh 45 pounds. So I could go to this company and say, well, look, with 90% confidence, I can tell you that the product you're producing doesn't weigh what you say it does on average, right? The true mean is not what you think it is. It's going to be something a little bit higher. Now, this seems pretty inconsequential. We're talking about the weight of plates that you work out with. But this could be the weight of, I don't know, a beam that supports certain structures, right? Or I'm producing some type of medication or a vaccine that's supposed to have a certain level of something in it. Or a lot of times actually where a lot of companies get liable is with like the weight of products, like saying they weigh a certain amount or have a certain amount of, of weight that they can hold is like with children's toys or children's cribs and things like that. So this is applicable to very real world applications. Really any product that you can produce that needs to hit a targeted weight or needs to hit a targeted kind of strength measure. And in this example, you could say, go to the company and say, well, look, with 90% confidence, I can tell you, you're not hitting, your true mean is not where you want it to be. Like you need to adjust your production process. Add some more, I don't know, iron in there, or not iron actually, take some out. Put something lighter in there because you're missing the target a little bit. Now, let's say instead the company comes to me and says, well, look, yeah, you're saying, you can tell me this with 90% confidence, but could you tell me this with 99% confidence? Well, I go, well, alpha there is 0.01, right? Before, when I wanted an alpha of 0.1 in the tails, these are my z-scores. So what has to be true if I want 0.01 total in the tails? Well, my z-score is going to have to be kind of out here somewhere, right? So my z-score has gotten larger. If my z-score has gotten larger, what happens to my confidence interval? It's going to now be wider, right? So if it was already at 45.11, my guess is if we work through the math, my new lower and upper bound is going to be somewhere out here. And now with 99% confidence, I could say, okay, 45 pounds could be one of the true means, right? I can't tell you with 99% confidence that it isn't. But with 90%, I could tell you it probably isn't. And honestly, if I'm a company, I look at that and I'm like, oh, 90% is still pretty high. 99, yeah, you can't say with 99. What can you say with 99% confidence, right? But with 90%, that's a pretty high level. I might want to kind of re-look at my production process there. So this is kind of the interpretation of our confidence rules. We can start to think about how we can use them to make certain statements and decisions. Okay? Any questions on any of that? I know I kind of went back and forth to kind of the old work there to kind of show what would change. Okay. All right. If there's no more questions, we'll probably end there for today. So what I'm going to do, I'll get an online quiz up that'll be due before we meet on Wednesday. I'm going to get back to my office. Like I said, that Excel assignment will probably be coming either after class Friday or not till after class next Monday. Just depends on how quickly we kind of get through things. But its due date will be way off in the future, right? So we'll be working with Excel pretty much probably most of the class on Wednesday, to be honest. We might revisit doing some stuff by hand at the end. But we'll be using Excel a lot. I think there's some things I think for most of you, there's some things I can show you in Excel that will make the confidence intervals make a little more sense or give you a data justification for it. Okay? Other than that, you've got the current connect assignment. That'll be due at the end of the week this week. So start kind of working through those. Get any questions you have to me as early as possible. And other than that, if there's no more questions from me, I'll see you on Wednesday.